really what we're going to be looking to do here so again, I'm going to decimals up number 1 with you watching. We're going to, for number 1, be changing only the constant. So our base is going to be x squared, which is, how do we know x squared is quadratic? It's squared, right? Okay, and then we're going to mess with only the constant, and then our job is going to be to come up with a rule or an observation of what happens when we mess with that constant, okay? So you're going to do the same process for 2, 3, and 4 in a moment. All right, I got to go to decimals, graphing, calculator. And I've got another function in there still. So you're going to start with just x squared, and shift 6 will, I put a 6 in there. Shift 6 will give you your exponent. And I'm going to go to that view. So here's my x squared parabola. My constant is 0 right now, okay? So what we're going to do next is we're going to add a constant to it. So I'm going to say x squared, and then who would like, someone give me like a constant that I can add to this. That's Sean? Plus 4. And so that green one is the parabola when I add 4. I'm going to do x squared minus something. Who's got a number for me to subtract? Yeah. 3. Minus 3. So that purplish one is the same thing but minus 3. I'm going to do one more. You guys want to hit that? Who's got one for me? I don't care if it's plus or minus. JP? Plus 5. So x squared plus 5. Threw it way up there. So what I want you all to do now, number 1 in your notes, is explain how you're seeing the parabola change. Remember this blue one right here? That's the OG. Okay? So what is changing the constant doing to our parabolas is your job now. So number 1 in the notes, we'll go summarize this. You're telling me that adding the constant is changing y-intercept, which we already know that number is the y-intercept from things we've done. And then parabola stays same shape, right? We also use the word, it's a translation. We're only sliding it up or down. That's all that constant's doing. Same parabola, up or down, yeah. Your job now is to change your leading coefficient to a number greater than 1. Change your leading coefficient to a negative number with an absolute value, 1 or greater. And then change your coefficient to fractional coefficients. And each time you're going to come up with this general rule of how this is impacting our x squared function, okay? Just like we did with the y-intercept. So the second big idea is changing the leading coefficient, right? To positive numbers. So someone give me a coefficient to test versus my x squared. Yes. 8. Woo. Okay, so it appears as though I increased my coefficient and my parabola got more narrow. So let's test that. If I were to pick a number between 1 and 8, it should be in the between those, right? So what's one, Kyle? Give me one to try.
7.
7. Let's see. Should be a little less narrow, right? Well, it's hard to see. Let's try another. Let's try 4. Less narrow, right? It's in between. Okay? And let's try one that we know would be more narrow than 8x. Who's got one for me? More narrow than 8x. Taking this next level, Sean. 10x, this should be the narrowest, correct? Our theory proves to be true. The larger the leading coefficient, the more narrow. Now, let's talk about why. Any ideas why? No, it is how it works, but there's a reason why it works like that. Here's the reason. Let's look at input 2. So if we put 2 in, our x squared, which has our lowest leading coefficient, that's going to have the lowest output because it's times 1, right? We can't even see the rest of this thing right now. But what's the next parabola that's going to hit? Which color? If I keep going up. Definitely purple. What's the second highest leading coefficient? Purple. Okay, what is it going to hit after purple? Green. Because it's the second from highest leading coefficient. Which one would have hit last? But, because it's the narrowest. Now, so narrow kind of looks like small. Would you agree? But the narrowness is actually happening because for the same input, it's higher. You guys understand what I'm saying by that? Let's zoom out a little bit. For the same input, it's actually higher. Right? So for this input here, it was 2. If I keep that input, I'm going to hit purple next. It's narrower because things are getting bigger quicker. Does that vibe? Okay, what's the next thing you had to do? Negatives? Is that next? Look, watch what happens when I make these negative, friends. I'm going to keep my x squared on there. What happens when I change them to the negatives? Yeah, a reflection happens, right? So that's another big idea. Are they wider or narrower than what they were when they were positive? No, same thing. So I'm going to see if I can make an image on here, how Caleb kind of explained it. Let's see here. So Caleb kind of got some ideas from this one and the last one where there's fractional. Or if I had 1/2 x squared, right, it's wider. So let's talk about the smaller than 1. If when it gets to be a bigger number, it gets narrower. When it gets to be a smaller number, it makes sense. It's going to be wider. So here's 1/10 x squared. Let's say 1/1000th x squared maybe. We're getting smaller and smaller. Okay. That almost looks like it's flat, right? And flat would be 0x squared because it's just x is 0. You good with that? So if I'm going to go negative now, further than flat, I would have to go negative, right? Check that out. There's that negative happening. It has to you can't go flatter than flat. So when we start going negative, it's the same thing, just below. You guys seeing this?
Yes. Yes. Oh.
So, when we're talking about how narrow it is, we're talking absolute value, right? An 8 and a negative 8 have the same narrowness. The positive 8 goes up, the negative 8 goes down. So now I've heard some of you talking with your Khan Academy unit, like, what does it mean when it says opens up or opens down? So we're going to simplify some of that language. The positive ones open up, the negative ones open down. So let's get back and make sure we can synthesize all of our big ideas. And what's so cool is, when I was in school, man, the teacher just wrote down bullets and you had it. You guys actually found it for yourselves using Desmos. So when he talked up here, changing the constant just shifts us up or down. Okay? Then we saw that the larger the leading coefficient, the narrower. And that's because our outputs are increasing quicker. We saw that the negative reflects across the x, right? That mirror image, it opens down. And then we saw that the smaller the absolute value, the wider the parabola. Those are all of our big ideas. And just like our warm-up where we could compare those lines, now we could compare parabolas based on features of their leading coefficient and their constant. Next, you know how we're all about multiple representations. You're going to justify the same idea using some tables. So similar functions and tables, we're going to compare and contrast inputs and outputs now to justify this idea. All right, y'all, I'm ready to fill this out. So, for the top table, if I have x squared plus 10, I've got 19, 14, 11, 0, 11, 14, 19. I just messed that one up. Good point. 10, 11, 14, 19. So, you'll notice that there's a mirrored image. Why is there a mirrored? Why are the numbers? It's quadratic, which means I have an axis of symmetry and things are the same on both sides. Okay? So minus 3 is going to give me 6, 1, negative 2, negative 3, negative 2, 1, 6. So we need to use these numbers to explain why the parabolas have the same narrowness but are just shifted up or down. So every one of these is 3 lower than every one of these. You agree with that?
Yeah.
And every one of these is 10 more than every one of these. Here's how we prove that they're the same narrowness or width. From here to here, how did it change? -5. What about here to here?
-5.
What about here to here?
-5.
So the changes were all the same. Let's look somewhere else. What about from here to here? -1, -1, -1. So same spot to same spot, the change is the same. It's almost like, it's not linear, but it's almost like parallel lines kind of, right? Almost kind of like that idea. So let's look down at the leading coefficient. We know as the leading coefficient gets bigger, they get narrower now. These shouldn't be shifting up or down because there's no change in the constant. And we know the negative should flip us, right? So if we double, we got 18, 8, 2, 0, 2, 8, 18. Half would be 4.5, 2, half, 0, half, 2, 4.5. And times -2 is -18, -8, -2, 0, -2, -8, -18. And so we're going to justify this as, check out that smaller leading coefficient. I got smaller outputs across the board, right? Which is going to flatten out my parabola. I got that larger leading coefficient. The numbers are bigger, right? We got those 18s. That's meaning narrower. And then what happens when there's the negative? My outputs are all negative, which means below the x, right? My y is below the x then. So we have pictures to justify it in our graphs that we showed on Desmos, and now we have the numbers to prove it. What you're going to need to do before you start your homework today is a card sort. All right? And I'm going to do one of the piles, an example of what you might need to do, okay? This won't be one of your piles. But really what you're going to have is you're going to have something like a factored form that might be something like x plus 2, x minus 4, okay? And that means you'll have a standard form that is x squared minus 2x minus 8. And then your explanation of why your graph is what it is would say something like y-intercept is -8 because the constant. And then you would say the x-intercept is -2 and 4 because of the factored form. So it's kind of our warm-up, actually. So -8's down here, a -2, and a +4. Something's not right. Oh, y-intercept. That doesn't have our vertex in it, but something like that. You're going to pull out meaningful things from your equations as you make your match. So each pile will have standard form, factored form, graph. 3 things in each pile, and then you need to prove why your graph is the graph.